What if I told you that the single most complex machine ever built by humanity isn't the Large Hadron Collider, and it's not the International Space Station either? In fact, it's a machine that sits in a clean room in the Netherlands. It costs over $400 million per unit, and without it, our modern world basically collapses. It's called an EUV lithography machine built by a company called ASML, and honestly, it shouldn't exist. The engineering required to make this thing work is so ridiculous, so borderline impossible, that for 30 years almost every expert said it was a dead end. They said it was a waste of money. They didn't just say it was hard, they argued it was physically impossible. But today, this machine is the only reason your new iPhone is faster than the old one. It's the reason AI is exploding. It is the bottleneck for the entire global economy. If these machines stop running, Silicon Valley stops running. So how did we build the impossible? And why does the future of humanity depends on shooting a laser at a drop of molten tin 50,000 times a second? Let's find out. To understand why this machine is such a big deal, we have to talk about the problem it solves. You have probably heard of Moore's law, the idea that computer chips get twice as powerful and cheaper every 2 years. For decades, we kept this going simply by shrinking the transistors. Smaller switches meant we could pack more of them onto a chip. Easy, right? Well, it was easy until we hit a physical wall. We were using light to print the pattern of these tiny switches onto silicon wafers. Think of it like a really fancy stencil. You shine light through a mask and it touches a pattern. But eventually the transistors became so small that the light wave itself was too chubby to draw the lines. Imagine trying to draw a detailed portrait using a fat permanent marker. You can't just get the fine details. We needed a finer tip. We needed light with a much smaller wavelength. We needed extreme ultraviolet light, or EUV. But here's the catch. EUV is a nightmare. It gets absorbed by everything. Air absorbs it, glass absorbs it. You can't even use normal lenses to focus it. To work with EUV, you have to reinvent the entire concept of optics from scratch. And that's where things get really crazy. The first problem was, how do you even generate this light? You can't just buy an EUV light bulb. The solution engineers came up with sounds like something a sci-fi writer would make up while having a fever dream. Here is exactly what happens inside this machine. A generator shoots a microscopic droplet of molten tin, yes, the metal tin, across a vacuum chamber at hundreds of miles per hour. As this droplet is flying through the air, a high-powered CO2 laser blasts it. But it doesn't just blast it once. The first pulse is a pre-pulse. It's a gentle tap that flattens the droplet into a pancake shape. Then, microseconds later, a main pulse hits the pancake with incredible energy, vaporizing the tin into plasma. That plasma glows, and for a brief instant, it emits EUV light. Now that sounds hard enough to do once, right? But to get enough light to print chips, this machine has to do that 50,000 times per second. Let me repeat that, 50,000 times a second. It is hitting a moving target microscopic in size twice with perfect timing, continuously for weeks on end without missing. If the timing is off by a fraction of a nanosecond, the machine fails. It is arguably the most precise shooting rally in the universe, and somehow it works. Okay, so you have made the light, now you have to focus it. But remember, EUV light is absorbed by glass, you can't use lenses, so you have to use mirrors, but not just any mirrors. These mirrors, made by Zeiss in Germany, are widely considered the flattest surfaces ever made by humans. To give you a sense of scale, if you took one of these mirrors and built it up to the size of the entire country of Germany, the biggest bump on the surface would be less than a millimeter high. If you scaled it to the size of the Earth, the biggest imperfection would be about the size of a golf ball. These mirrors have to be coated with incredibly thin layers of silicon and molybdenum to bounce the EUV light just right. And because the air absorbs EUV, this entire process, the tin shooting, the plasma, the bouncing of mirrors, has to happen inside a near perfect vacuum. And while all of this is happening, the machine is moving the silicon wafer around to print the chips, and it moves fast. The acceleration forces on the wafer stage are higher than a fighter jet taking off, but it has to stop with an accuracy of less than 1 atom. It is like driving a Formula 1 car at top speed, slamming on the brakes and parking it exactly, and I mean exactly, in a spot defined by the width of a human hair split 10,000 times. The craziest part of this story isn't the physics, it's persistence. In the 1990s and early 2000s, huge companies like Canon and Nikon were the king of chip making machines. They looked at EUV technology and said no thanks, it was too hard, it was too expensive. They thought it would never work reliably enough for mass production. But ASML, a small European company, went all in. They spent billions. They collaborated with researchers, governments and suppliers from all over the world. It took them nearly 30 years to get this from a lab experiment to a factory floor. There were moments when they almost went bankrupt. There were moments engineers thought they had wasted their life, but they kept pushing because they knew that without this, the digital age would stall. Today, ASML is a monopoly, not because they bought out their competitors, but because their competitors gave up. If you want to make a cutting-edge chip for an iPhone, a Samsung, or an Nvidia AI processor, you have to call ASML. There is literally no one else. So the next time you scroll through your phone, or ask an AI a question, or play a high-end video game, take a second to appreciate the absurdity of what's happening in your hand. You are holding the result of a machine that shoots laser at molten tin 50,000 times a second, bouncing invisible light off the smoothest mirror in the universe in a vacuum with atomic level precision. We often think of technology as magic, but in this case, it's not magic, it's hard work, determination, and it is really ridiculously good engineering. If you like this video, please subscribe and thanks for watching.